This is the MAT125 lesson number 6 on predicates and quantifiers. We start with a definition. A predicate is a sentence that contains a finite number of variables and becomes a statement when specific values are substituted for those variables. The domain of the predicate variable is the set of all values that may be substituted in place of that variable. In other words, something like q of x would be an example of a predicate. It's a statement like something like x is even. That's an example of a predicate. It's something that would be true or false depending on the value of x. Now we have a symbol that looks like an upside down A, and it's the Universal Quantifier. It denotes the phrase in English where we could say for all. That's typically the way that you would read that, but there are other expressions in English we could use. Some other expressions that can be used are instead of the expression for all are the following. For example, you could say for every, for arbitrary, for any, or for each, or given any, like given any real number x, and then some predicate involving the real number x. So then moving on, we have a definition to work with. If we have some predicate q of x and some domain d for that variable x, a universal statement is a statement of the form for all x element of d, q of x. Let me say an example right here. Like when we say all dogs go to heaven, this is a universal statement, and we could put it in very formal language like this. We could say D is the set of dogs. And so in this formal language, we say for all x element of D, that is anything that is in the set of dogs, we'd have to say Q of x is the statement x goes to heaven. So let me just add that in. So I could make these definitions here. D is the set of all dogs. Q of x is the predicate that x goes to heaven. And then we could put it in formal language that for all elements of the set of dogs, Q of x is true. That is, so what I'm talking about is a sort of mathematical and logical language in which I can make a statement that's a universal statement. I can say all dogs go to heaven in a very formal and set theoretical and logical way. For every element of the set of D, Q of x is true, where Q of x is the predicate that x goes to heaven. So we'll finish off that definition statement. The universal statement is defined to be true if and only if Q of x is true for every x in the set D, and it's defined to be false if and only if Q of x is false for at least one x in the set D. So if there was one dog that didn't go to heaven, this would be false because there exists some x where the predicate isn't true. Okay, so let's take another example of this same kind of thing, a universal statement that uses the universal quantifier. This one says, consider the following statement where R is the set of real numbers. Find a counterexample. So the universal statement says for all x element of the real numbers, x squared is greater than or equal to x. And at first that might sound true. You think, wait, if you square something, wouldn't it be bigger? But actually it isn't true. There is at least one x where it isn't true. In fact, there are infinitely many, but you can say this statement is not true because there is a counterexample. What is the counterexample? Well, there are infinitely many. Anything between 0 and 1 would actually work. Let's take x equal 1/2. That's a counterexample. Why is that a counterexample? Well, it's a counterexample because x is, in fact, a real number, or I should say specifically 1/2. When x is 1/2, it is a real number. It's an element of the real numbers. So I could say 1/2 is, this is justifying why it's a counterexample, because it is a real number, and 1/2 squared is 1/4. And 1/4 is less than x, which is 1/2. So the statement that squaring it is greater than the value isn't true. In fact, just the opposite. It's strictly less when you square it. If you begin with the number 1/2, it's less than the value you began with. So that's the counterexample. Okay, moving on. The symbol that is here is called the existential quantifier. It looks like a backwards E, denotes the phrase in English, there exists, or some is another way to say it, or at least one. Usually we'll just read there exists because that's just kind of maybe habit or convenient. But logically, there are other ways to say it. So some other expressions in English that might come about naturally, but then you can uh, turn into the formalized symbol. You might see there is a, or we can find a. These are ways that you might speak in everyday language, but then or informally about mathematics. But then if you were to speak informally about mathematics, then you could write it formally in this notation. So if you say there is at least one, you just say some or for at least one. Some examples of that in English, we could say the sentence there is a student in MA125. Um, that's actually true, and it could be written a little more formally as there exists P element of capital P such that P is a student in 125. It's not totally completely formalized because I might create a set of all students at school or in college or something like that, but we did formalize the set P of all people, and that's why this notation can be written in that formal way. P is an element of the set of all people. So if you're an element of the set of all people, there exists some element of the set of all people such that that person is in the class 125. You could say that it's right here that we have some predicate right on the variable P, and it's true because there is some student in the class 125. Hopefully still. Hopefully they will still be true at the end of the semester. Let's move to the next definition here. Let Q of x be a predicate and D the domain of the value of the variable x. An existential statement is a statement of the form there exists x in D such that Q of x is true. It's defined to be true if and only if Q of x is in fact true for at least one value in D, and it's false if and only if that statement Q of x is false for all of the values in D. Let's take a look at some examples. A says, consider the statement there exists M element Z plus. So Z plus refers to the positive integers. So there exists some number element that is an element of the positive integers such that when you square it, you get the number itself. Well, in the positive integers, is there any number that when you square it, it's equal to itself? Well, yeah, of course, 1. If you square 1, you get the same thing. So this is actually, in fact, a true statement because it is true for at least one value in the set D. The set D being here, this guy. The Z positive, that is the D in this particular example. And so I would say that this existential statement is true because there, in fact, there is one element, 1, right? This is true because 1 is an element of the positive integers, and 1 squared is equal to 1. But if we change the set D, or rename and just say some set E on which we have this um, existential quantifier being used, well, the set E is just the numbers 5, 6, 7, 8. So we consider this statement, there exists some M element of the set E, which is here, such that when you square it, you get the value you started with. Well, that's actually false because it's false for every element of E. Because for all values m that are elements of the set E, m squared, it won't be equal to m. If you take any of these values and square it, you won't get the same thing. So it's something I want to point out, how you can simplify a statement that has this form into a statement that has this form. If we say, for every x that's element of the set U, if p of x, then q of x, that statement is true, it's logically equivalent to just saying, for every x element of some other set D, q of x is true, by just narrowing the set U to be just the domain D, consisting of all the values of the variable x that actually made P true. Maybe I could draw a picture that sort of illustrates the principle of that comment. So we might begin with some larger set U, and let me draw a set P and a set of elements Q, and we can sort of visualize this as saying that you could take any x in the set U. If P of x is true, I, I mean in the picture that you would be in the set that I draw here where for P. If P of x is true, you must have some x that is in this set. So if you said this statement is true, if P of x is true, then you would certainly be in the set where Q of x is true. Well, this is the same thing. These are the same statements because what I could do is just say, rather than using the set U, I could just say D is the set of all values where P is true. So if I am restricted to elements in D where P of x is true, then certainly Q of x is true. Similarly, a statement of the form, there exists x such that P of x and Q of x is true, that can be written as there exists some x element of the set D such that Q of x is true, where D is just the set of all x's where P is true. Okay, so I can construct a picture to sort of illustrate this principle as well and how this simplification is true. Imagine that we had a set where there is a set P and set Q that look like this. And the original statement, let's look at this, says there exists x such that P of x and Q of x are true, which means that that x would have to be here in the way that I'm visualizing these statements, that those x's that are in this region make P and Q both true. Well, we could rewrite it to say that there exists x, an element of D such that Q of x is true, where D is just the set of all x's where P is true. So in other words, you could just rename this set D. So whereas the original statement said there exists some x in some larger like universal set, we reduce instead of referring to the just arbitrary or larger universal set, if we just said some smaller subset D, I could say there exists some x element of the set D such that Q of x is true, where D is just those elements where P of x is true. So that's the idea. Here's an example. You could begin with a statement, there exists x such that x is even and x is prime, and we could change how it's stated in a way similar to what's happening here to just say, let's, rather than just saying there exists some number, we'll say let E be the set of even numbers. And then we could say that there exists x element of the even numbers such that x is prime. Okay, so now we'll move on to looking at negations of universal statements. The negation of a statement of the form for all x in D, Q of x is logically equivalent to a statement of the form there exists x in D such that not Q of x. Symbolically, this is the negation of this universal statement is this existential statement. So let's look at an example. Write a negation for each. Well, The first one, all customers are happy. We could say in just everyday language, informally, we could say there exists a customer that is not happy. To write this in some kind of formal notation, we might do something like C is the set of customers. And we might create a predicate that is um, X is happy. So that would be true or false depending on who that X is. And so we were given some statement, all customers are happy. We could say that the negation in a formal language is there exists X element of the set of customers where not Q X is true. So here's another universal statement. Every number is a rational number. So a negation would be there exists a number that is not rational. Notice I did this in a previous video, but there's kind of some rules about how to do negation. So a negation of all is some are not, or at least one is not. So these guys are negations of each other. A negation of none is some, or at least one. So what we have here is an all numbers are rational numbers. So there's the negation, some are not. There exists a number that is not rational. And I could write it in a kind of formal language where I can use the set Q is a set of rationals. We might say there exists X. X is not an element of Q. Number 3 says for every X in the real numbers, X squared is greater than or equal to X. And that's actually not true. We've already seen that in an earlier part of this video. So now we can write something that's actually true by forming a negation. Let's write the negation in formal language. The negation would be there exists some X element of the real numbers. And then the negation of that statement would be X squared is less than X. You notice how because this was a greater than or equal, so to negate that, I have to put just a less than. If that had been just a greater than, it would have been a less than or equal in the negation. So now let's move on to negations of existential statements. We have that the negation of a statement of the form there exists X in D such that Q of X is true would be logically equivalent. The negation is logically equivalent to a statement of the form for all X in D not X, or not X is true. So to negate an existential, you get a universal, whereas you just saw negating universals gave me existential quantifiers. Symbolically, the notation is the negation of this existential statement is this universal statement. Let's take some examples. Write negations for each. So we could begin with number 1, some problems in logic are not difficult. So this is like saying there exists a problem in logic that is not difficult, and we want to negate that. So really, we'd have to say that uh, that all logic problems are difficult, because here is the negation of that. Right? I'm going back to my rules for negating quantifiers. If we have a statement that some are not difficult, the negation is all of them are difficult. Right? And to negate some would be to say no or none. All right, so we have this given, some are not difficult, and the negation is all of them are difficult. Let's find a way we can put that into a sort of formal language. Let's say something like P is the set of all logic problems. So any particular logic problem could be some element X that belongs in the set P, and then we could say a predicate is like why don't we take, well, let's say dx is difficult. I think that would be sufficient to say in the context here. So if this, for a particular problem x that belongs in the set P, to say the predicate d of x is really just saying this particular problem is difficult. It could be true or false. That statement is true or false depending on the actual value of x, whether it's one particular problem or another. So maybe sometimes true, maybe sometimes false, but what we're looking at now is maybe, why don't we state what was given? What was given is some are not difficult. So what was given was there exists x element of the set of problems where uh, negation of d of x is true, right? Because there exists some problem where difficult is not true, right? And then the negation of this existential quantifier would be a universal quantifier. We would say for all x, all problems in the set of logic problems, difficult, difficult, uh, the logic problem x is difficult. D of x is true. So there are, the answer is written two different ways. This is the answer, informally, sort of everyday language. And this is the answer written formally. Second example, the given statement is there exists at least one solution to the equation x to the fifth minus 4x squared plus 7 equals 0. So we want to write a negation to that. So just sort of informally in everyday language, or a sort of pseudo, in a sort of mathematical language, we could say to negate there exists a solution, we would say there is no solution. So to put that in a sort of formal language, I would do something like, I need to use the universal quantifier, and so I would have to say something like, for all x might do element of the real numbers. Uh, you don't necessarily have to say that. It doesn't necessarily say that we're referring to the real numbers. So let me take that out. It's nothing in this statement meant that we had to assume real numbers. So we'll just say for all x, meaning numbers, for all x, and then we could negate this statement by just saying x to the fifth minus 4x squared plus 7 not equal to 0. So that is, there's no solution for all x's. So there, this can be made more precise by specifying some domain. Do you mean all integers, all rational numbers, all real numbers? So that could change whether or not this actual statement is actually true or false. So that would really be relevant in if we were really working with this statement mathematically, whether x belonged to the set of all real numbers or rational numbers or integers or what. But just to kind of get the sense of the formal language here, because this said there exists at least one solution, I'll say for all x, meaning values that, obviously describes potential solutions. For all x's, this is not true. So in other words, there is no solution. Let's take a look at number 3. For some real numbers x is even and x is divisible by 3. So how do we negate that? Because it began with an existential quantifier, we'll form a negation with a universal quantifier. So actually, we could first of all just write it in sort of informal language so that we can, because that might be easier at first, right? So this says for some real numbers x is even and it's divisible by 3. So the negation is no, for no real numbers. There are no real numbers. Well, actually, this negation is actually false if you were wondering about it. You could take 0 as being even, but also divisible by 3. Well, let's see if we can put that negation into a kind of formal language. So say something like, for all x element of the real numbers. Well, so this is a way to negate it in everyday language, but to use the formal notation, what I want to do is say um, I have to switch this to a universal quantifier on x. So I'm going to say for all x's, and then I'm going to try to negate this guy, which to negate this, I'll say x is not even or x is not divisible by 3. I'm using De Morgan's law. X is not even. That doesn't mean it's odd. It's just not even. It could be a decimal. X is not even or x is not divisible by 3. So whereas in the everyday language, I could begin with another kind of way of expressing the universal quantifier, which I'm saying there are none, there are no real numbers. We don't really put that, we don't write it that way formally. What we say is for all numbers, this is not true. This is not true, which means this is true. So this because this is the negation, right? I'm using De Morgan's law. That's one of two laws of logic that are called De Morgan's laws. Let me just review something that was just happening in those last few examples. If we were negating the word sum in informal language, in really everyday language, the negation of sum is none. But what happens when I switch to formal language? I don't really have a symbol for none. I do the universal quantifier, which is for all, and then I just say for all, and then I put a negation on the statement. So let me see if I can just give a real simple example of a point that I'm making here. Um, suppose you had some dogs go to heaven. So the negation in everyday language, no dogs go to heaven. However, in a sort of formal language, I would change that. We could make it sort of formal, like D is a set of dogs. And we would say, uh, we'd have to have a predicate like QX is X goes to heaven. And then we could put it formally like for all X element of D, not Q of X. So we could read this as for all dogs X, X doesn't go to heaven. Okay, let's move on to creating negations of universal conditional statements. So a conditional statement like for all x, if p of x is true, then q of x is true, can be negated. That's what the tilde here says. And to negate this universal conditional, we'd say there exists some x such that p of x is true and not q of x is true. Let's look at some examples. So first, maybe in an informal language, this would be you are a person who finished dinner and you cannot have dessert. That would be negating this conditional. Notice there's no if in the negation of the conditional. Putting it a little bit more formal uh, into a, making it more formal, let's say P is a set of people. Maybe they're the set of people at the dinner table. So what was given was a conditional that if you are in the set of people who finish their dinner, then you can have dessert. Let's say, so let's create also some predicates that we could use. So d of x is the predicate x finished dinner. And let's say x is the predicate that x can have dessert. So why don't we look at this first of all, just what would happen if we put the original given statement in formal language. Right? So what was given was really something we could cast as a universal conditional in the sense that we could say, for all x element of people, if you finish dinner, then you can have dessert. This is saying if you're a person and dinner is finished, that implies you can have dessert. So what would be the negation? The negation is there exists somebody, dinner is finished, dinner is finished, and they can have dessert is not true. See how the negation of the conditional is an and statement. This is like saying there exists a person X such that X finished dinner and X cannot have dessert. All right, so let's do a negation for this one. The statement says for all X element of the reals, X less than 1 implies 1 over X greater than 1. Well, first of all, the fact that it says implies means that we have a conditional here. In the conditional, this is the statement P, and this is the statement Q. And writing the negation of a conditional, this is more formally a universal conditional. Let's write the negation in symbolic form. The negation would be there exists some X element of the real numbers. And then what you're going to do is P and not Q. So P is true, and then the negation of Q would be 1 over X less than or equal to 1. Now, this is something that's worth taking a minute just to analyze whether this statement was actually true or whether the original was actually true. It might at first seem that this first given statement was actually true because if you think of something like maybe 1/2, take a number that is less than 1, like 1/2, and if you put that in for X, you'd have 1 over 1/2, which is 2, and that makes something greater than 1. And so maybe there you might try a value and say, well, it seems to be true with 1/2. And if you plug in 1/3, if X was 1/3, 1/3 is less than 1. And 1 divided by 1/3, that's actually 3, which is bigger than 1. It might at first seem to be true, but this says for all X elements of the reals, and the thing is that you could actually take a negative value. You could take something like -2, and -2 is less than 1. But if you put 1 over -2, that's -1/2. So this would actually be false. And so this is actually the statement that is true. There is a X value in the real numbers that is less than 1, but 1 over X, let's say 1 over X is less than or equal to 1 also. For example, X equal -2. That would be a counterexample to the original universal statement up here. X equal -2 is a counterexample. It's a counterexample to the given statement. So in actual fact, this statement is actually true. This statement was actually false. Let's look at this thing called the 4-card problem. Suppose each card below has a number on one side and a letter on the other. This is given information. This is very important to recognize. It says, and we're assuming that's true, it has a number on one side and a letter on the other. So that is not violated in any of these. We assume that that's true. There's a number on one side and a letter on the other. So then which of these cards must be turned over, logically speaking, if we want to know whether the statement below is true or false? The statement that's given is, if there's a val on one side, then there's an even number on the other side. So think about that for a minute. Now, which of these cards do you have to flip over to see if this is true or not? Well, the answer is you have to flip over this one and this one. This one because you're going to confirm the statement is true, and this one because you're going to basically confirm if it's not true, or let's say disconfirm. By that I mean check if not true. So here you're checking if it's true, and here you're checking if it's not true. It's easy to miss this one, and you might have been tempted to think that you have to check one of these, but Neither of these is logically required to flip over. Let's see if I can go through explaining why that is. So the statement we were given is if there's a value on one side, so we'll call that P, then there's an even number on the other side, let's call that Q, and let's look at when a conditional is true and false, because what we're given is a statement that is a conditional. So in the truth table for the conditional, 4 cases, both of these could be true. We could have true and false, false and true, or both of those two could be false. And I'm looking at the truth value of a conditional statement, which has the form P implies Q. In this case, it's true. In this case, the conditional is false. Here it's true. There it's true. So only in this case would we actually have the conditional being false. So as we go through and check each of these cards, there's the statement P. Then there's an even number on the other side. This is the statement Q. Looking at this one, you actually have, there's a vowel on one side because there's an A. So you do have to flip this one over because you want to make sure that the Q is not false, right? Because the P is true. And if Q is false, there's an even number on the other side. If that wasn't the case, if there was a 3 on the other side, then the statement would have been false. So you definitely have to flip that one over. That's no big deal. That's no problem. This one I don't need to flip over because this is not a vowel. And so if the statement P is actually false, then the whole conditional is true. It doesn't really matter what's on the other side. It said if there's a vowel on one side. So if there's the letter D on one side, it doesn't matter what's on the other side. This statement would still be true that if there was a vowel on one side, there's an even on the other. Okay, so you don't have to flip this one. What about this one? It has a 4 on one side, which is an even number, which means there is an even number on one of the sides. So we know that there must be a letter on the other side because that's what it said at the very beginning. It has a number on one side, a letter on the other. So I know there's a letter on the other side, and you might think, oh, I need to check to see if it's actually a vowel. But the fact that there's an even number on one side means that the Q is true, which means you're in this case or in this case, here or here. If Q is true, the conditional is true. It doesn't really matter whether there was a vowel on the other side or not. There could have been even the letter D on the other side. And this statement would still be true, that if there was a vowel on one side, there would be an even on the other, even if there was even numbers, even if there's an even number on the other side of like a D. So what I'm saying is that if this part is true, then the whole statement is true regardless of whether there's a vowel on the other side. So don't have to flip. But then this one you do have to flip because what we have here is even number on one side is actually false. So now we're in the case here. I'm right back in this case because Q is false. There's an even number on the other side from the letter. This is not an even number. So this Q is false. And since it's false, I actually have to check to make sure that P is actually true, that there actually is a vowel on the other side. So you'd actually have to flip this one to check if the statement was not true. I mean, this is exactly the case where we have to check to see if it's false. If there was a vowel on the other side, it would be false. It's just something about the way the human brain works that we are pretty quick to recognize a situation where we have to check if something's true, but not as ready and to check if something is not true. It's a sort of confirmation bias that we have just naturally the way the brain works. It was hard to spot this right away as something you need to check. And also just how these are not necessary. It's not necessary to check these. It's sort of purely logically that's the case, but it's sort of hard to see in this really abstract case, which brings me to another example of the same question, but when it there's something about the way the brain works that it's really easy to do the same logic in this case, because the logic here is something that sort of your brain is sort of naturally designed to do to catch somebody sort of cheating. Uh, And so even though we think that we're logical, we really aren't as logical as we think. We're just sort of trained where nature gives us some advantage to see things logically in some cases. For example, here. So suppose the same four cards instead showed a person's age and what they were drinking at a party. Which cards do you have to flip to determine, logically speaking, if the following statement is true? If a person is drinking alcohol, or if a person is drinking an alcoholic beverage, then they are of legal drinking age. So which cards do you have to check? Well, it's trivial. It's obvious. You got to check this one, make sure that that person is of legal drinking age because that's an alcoholic beverage. It's a beer. You don't need to check this one. You don't need to check this one. Uh, this person isn't drinking alcohol, so it doesn't matter what age they are. And this person is 25, so it doesn't matter if they're drinking alcohol. But you do need to check this one because that's a 16-year-old person. We need to make sure they're not drinking alcohol to confirm that this is actually true. So something about that, the way the brain is just sort of programmed to check to make sure everybody's following the rules is sort of a social thing that we have our brains sort of well attuned to do, whereas thinking in a purely abstract way, we don't really have we have to train ourselves to do that. So that's what that example really illustrates well. Okay, so let's move on to how you can uh, form contrapositives, converses, and inverses for universal conditional statements. So given a universal conditional, that's what I have here. For all x element of the set D, if P of x is true, then Q of x is true. The contrapositive would be for all x element of D, if not Q of x, then not P of x. Converse would be for all x element of D, if Q of x, then P of x. And finally, the inverse is for all x element of D, if not P, then not Q. Let's take an example. For any integer x, if x squared is even, then x is even. Let's form the contrapositive, converse, and inverse. Well, in a formal notation, I would say for any x element of the integers, it's a symbol for the integers. With the contrapositive, I would say if x is not even, then x squared is not even. Well, actually, you could say because I have x elements, this is for any integer. So if you're talking integers, then they are either even or odd. So it is also correct to say if x is odd, then x squared is odd. That would be okay because not even really means odd in the assumption that we're dealing with an integer. Now the converse, that would be for all x element of the integers if, now the converse you just change the order, so I would say if x is even, then x squared is even. And finally the inverse, for all x elements of the integers. And with the inverse, you leave it the conditional in the same order, but you just negate each of the components. So we could say in the same order, but negating if x squared is not even. You could say odd because we have integers only. We're assuming integers. So if x squared is odd, then x is not even. Or just say odd. Okay, done. One last thing is to translate back and forth between different variations on how we can write a conditional. We can use the words sufficient condition, necessary condition, and only if, and I think I'll do some examples here. Let's just write them in different ways and see how that goes. So basically the rule that I'm using is if I have a conditional which can generally be put in the form P implies Q, I could say P is sufficient for Q. In other words, I could say if P then Q, or P is sufficient for Q, or Q is necessary for P, or I could say P only if Q, or just if P then Q. So all of these are the same. Sometimes it helps to visualize the conditional as an Euler diagram or even a Venn diagram. So what I mean by that is like when you have P implies Q, put P inside of a circle like this and then Q on the outside. So if P is true, then Q would be true. So P implies Q in this picture. And all of these are describing this picture. I would say if being in the circle of P is sufficient to be in the circle for Q, and it is it's necessary for Q to be true if you're in the circle for P. So Q is necessary for P. In other words, like it's if I want to go to the set P, then it's necessary to be in Q, right? And this statement here is just saying you have P true only if you know that Q is true. And then if P then Q is pretty easy to visualize. If P is true, Q is true. So for this particular example, we could say if you live in Philly, so we would put Philly as the inside of the circle. So if you live in Philly, then you live in Pennsylvania. And so you could see that living in Pennsylvania is necessary for living in Philly, or you live in Philly only if you live in Pennsylvania. Let's take another example. It says if a number is divisible by 8, then it's divisible by 4. That's P. That's Q. So we have some alternate ways in which we could write that. So I know that if something is divisible by 8, that is sufficient to know that it is also divisible by 4. So having divisibility by 4 is necessary for having divisibility by 8. That's equivalent, logically the same thing. And a number is divisible by 8 only if it is also divisible by 4. All of those are the same. A picture of that, we've got divisibility by 8 as kind of an inside circle and divisibility by 4 outside because of the way in which this statement is and this is actually true, of course. If a number is divisible by 8, then it would also be divisible by 4. And so being divisible by 8 is sufficient, a condition for divisibility by 4. The divisibility by 4 is a necessary condition for being divisible by 8. And you could say that a number is divisible by 8 only if it is divisible by 4. So some equivalent statements we can basically what we're doing is we're writing the conditional in some alternate forms that are not just strictly using only if then. You could say something like this. Doing well in this class implies that you studied, or you do well in this class. The condition of doing well in the class implies that you studied. Okay, and then another way you might say it is doing well in this class is a sufficient condition to indicate that you are studying. I'm changing the wording a little bit to make it sort of more natural use of those words and still be logically the same. So what we're saying is that it's not saying that if you study, that's sufficient that you do well in the class. It's the other way around, is that if you did well, that's sufficient to know that you're studying. Doing well is inside of studying. Of course, somebody might be studying and not doing well, right? But if you are doing well, then we know that you're studying. And so doing well implies that you're studying, or doing well is sufficient to indicate that you're studying. And of course, you could say studying is necessary for doing well in this class. So let's finish off with one last example here. Finishing dinner is sufficient for having dessert. So you could translate that into a Venn diagram that it's a sufficient condition. If finished dinner is true, then you know that dessert is allowed. Having dessert is true. People that are in the circle of finished dinner, they can have dessert. So we can write some other equivalent, logically equivalent statements like finishing dinner implies you can have dessert. That's one possibility. How about this one? Using the phrase necessary. We could talk about a necessary condition and we could use it like this. We could say being allowed dessert is a necessary condition for having finished dinner. Like you could say you finish dinner only if you are having dessert. All right, I think I'll stop there with this video. I hope it's been helpful.